All right, let's get going here. Okay. Shall we discuss any homework problems? Yes? Number what? Number 7? Oh, the one with all those E's in it? Y'all ready? Everybody ready? Okay, so the instructions here, find where it's increasing and decreasing local max, local min, intervals of concavity, and inflection points. So let's start by taking the derivative. The derivative of e to the 2x is e to the 2x times 2. Plus, what is the derivative of e to the negative x? E to the negative x again times negative 1, because the exponent, you have to take the derivative of negative x, which is negative 1. That's chain rule, right? Are there any questions on that derivative? Okay. I'm going to need the second derivative also, right? Like later on in the problem, so I'm going to take it now. The derivative of 2e to the 2x, I'm going to get another 2 that's going to pop out of there. So it's going to become a 4e to the 2x. And then when I do the derivative of e to the negative x again, it's going to change signs again. So it's going to become plus e to the negative x. Is that too much, too fast, or are we good? We're okay? All right, there's our first two derivatives. Now, let's do trying to figure out where f is increasing and decreasing. What do we do to do this? What do we do to do this? Set the derivative equal to 0 and figure out where the derivative does not exist, right? Find the critical numbers, right? Critical numbers. So where's the derivative 0? Let's set 2e to the 2x minus e to the negative x equal to 0. My guess is this is where you might have run into a problem. So let me help you, because that's why I'm here. That's what that means, right? E to the negative x is 1 over e to the x. And what I'm going to do is get a common denominator, put the 2 together on the left. So imagine now that we have a 1 down here. So I need to multiply the top and bottom of this fraction by e to the x. So we get, I'll continue this up here. 2e to the what? 3x, right? Because I'm doing actually e to the x times e to the 2x. And so you add the exponents, x plus 2x is 3x. So that's what the top left becomes. Then I have minus 1 all over the common denominator, e to the x equals 0. You all still okay with this? Now, what? Okay. Did you take the natural log right here? That you could do. That you could do. Yes, that would be okay. But just as long as you didn't do natural log here on the whole thing, it would be okay if you move this over first. That's all right. So this right here, the only thing I have to consider is when the top is 0, right? This is an exponential equation. I'm testing my Math 1414 students on exponential equations on Thursday. So, this Thursday. They are taking a test. This would be a problem that I would ask on that test. So let's see how they do it back there in 1414. How do they do this? Move the 1 over, divide by 2. And how do you release a variable from an exponent? You need to come in with the log on both sides so you can drop it down. So I'm going to come in here with the natural log of e to the 3x equals whatever you do to one side, you must do to the other. And then now you can drop this down, drop the whole 3x down. What is natural log of e? It's 1. Natural log of e is 1. It's a property of logs. So natural log of e is 1. That's really just 3x equals natural log of 1/2. And then I'm going to divide both sides by 3. And that gives me x. I'm pretty sure that that is not the way it looks in the back of the book. Just like that? Yeah? Okay. Because, whoa, hey, easy, easy. Because if I were doing that, I'm looking at natural log of 1 over 2 as being natural log of 1 minus natural log of 2. That's a property of logs also. Remember, if you have division inside of a single log, you can split it into subtraction of 2 logs. And then what is the natural log of 1? 0. So this is really just negative natural log 2. Is that what it has in the back? So this, the back of the book might have this. Say again? Yes, that's the same thing, right? That's the same as negative 1/3 natural log 2. Now, there are other ways to do this, all right? One way that was suggested was to move this to the other side, which I agree, that works here. The only caution I would have on that is that if this had like 3 terms, that wouldn't work because you can't do the natural log on both sides if you have 2 terms on one side. So I'm just trying to show you a way that would be more general as a way to approach it. Okay, so we have that critical point. How about where the derivative does not exist? Is there anything that's going to mess this derivative up? Well, let me see. How about this version of the derivative here? Can you ever make this 0? E to the x? This is what e to the x, my 1414 class. E to the x looks like that. It's never 0. So you're never going to get division by 0. So that's our only critical point. So what I do now is draw a number line. On that number line, I put my critical number, negative natural log 2 over 3. Now, I need to kind of know where that is so I can pick some test points. So I'm going to get my calculator, and this is not my calculator. What is it? Okay, so this is about negative 0.23. That's just going to help me when I pick my test points to pick something on either side. So I like this one 0 on the right side. Over here, maybe negative 1. And I'm plugging these test points into the derivative, right? Test points always go into the derivative. So I go back to the derivative, which is here. And I plug in, let's plug in negative 1 first. So what would f prime of -1 be? That'd be 2 e to the -2 minus e to the -1. Are y'all following me here? Which is, this is the same as 2 over e squared minus e to the first power. Negative negative is plus. Positive 1 is the same as e, right? What's 2 divided by e squared? It's kind of a small decimal, right? If I subtract e, which is 2.718, this should be a negative number. So this is less than 0. That means that my original function over here is doing what? Going down. Then I plug 0 in. 2e to the 0 minus e to the 0 is 2 minus 1, which is 1, which is greater than 0. Positive means the derivative, right, is sloped up, so the original function is going up there. Questions? It looks like I have a local minimum, doesn't it? I just need to make sure that this value is in the domain of the original function. So did our original function have any problems? E to the 2x is exponential. You can plug anything you want into this. Same with this. You're never going to get division by 0 or square root of negative number. It's well-defined function. So since this number is allowed to be plugged in, it's part of my original domain. This should be a lowest point on the graph, right? Or locally, a local minimum. So where is f increasing? On the interval negative natural log 2 over 3 to infinity. F is decreasing on negative infinity to negative natural log 2 over 3. Local max. Do I have a local max? None. Local minimum. At negative natural log 2 over 3, right? Oh, sorry. And then I need the y value. So plug it into what? Plug this value into the original function. So how about I do it this way? E to the 2 times negative natural log 2 over 3, what was it, plus e to the negative natural log 2 over 3? Whatever that value is. Was that the original function? E to the 2x plus e to the negative x? Take this answer like this? Sure, that's fine. Have I addressed the issue of the question yet? Because we haven't even done the second derivative, but the second derivative would be the same process. The problem is in the second derivative? Okay. All right, so no questions here? All right, let's now look at concavity. For concavity, we look at the second derivative and we set that equal to 0, and we figure out where that's undefined. So repeating the process, kind of. So for concavity, you have the second derivative equal to 0 and where the second derivative does not exist. So second derivative equal to 0 means we're looking at 4e to the 2x, what was it? Plus e to the negative x equals 0. And I can see why you ran into a problem. There's no solution to this. So I would go through this the same way. I would get a common denominator. And because it's a fraction, I would just set the top to 0. Right, so common denominator, we did that just right a minute ago on the first derivative, same thing. Put them together, set top equal to 0. And I think at this step right here, we could stop. If you want to go one more step. Why am I done at this point? Why can I say there's no solution? Yep. E to the x, or e to the 3x, looks like an exponential growth function. It never drops below the x-axis, so it's impossible for it to be negative. Which means there's no places where the second derivative is 0, right? No places where it's 0. What does that mean to us then? What's that? There's no change in concavity. It never changes from a smile to a frown, which means what? It's one or the other always. It's either always smiling or always frowning. So it's good that you ran into this question because we hadn't run into one of these in class. So this means right here, since there's no solution, it's either concave up, this is what we did for concave up, or concave down always. Absolutely. What do we need our second derivative to be in order for us to be concave up? Second derivative must be positive, and to be concave down, negative. This told us it never changes signs. So all you need to do is look at the second derivative, which I think we could probably look at this one right here, and just talk about what its sign is. 4e to the 3x, that's always a positive number, isn't it? I add 1 to it, still positive. Divide it by e to the x, e to the x is always positive. This is always positive, isn't it? So the second derivative is always positive. But this is always greater than 0. Therefore, f is always concave up. Have I used the 3 dots therefore? Yes? In case you've forgotten, this means therefore. Therefore. Does that help now? It's always concave up. So the function goes down and then up, and it looks like a smile. So that kind of makes sense that it would do that, right? Maybe it almost looks parabolic, like a parabola. It was e to the 2x plus e to the negative x. Sorry? That was it? Okay. 3. Hey, that looks a lot like a parabola. And it has a local minimum here, right there. So let me graph a point here. Where does that local minimum take place? Well, someone on their calculator do negative natural log 2 over 3. Negative 0.23105. Yep, the computer just found the lowest point. And it found that the x-coordinate is negative 0.23105, which is negative natural log of 2 over 3. So we can feel pretty confident that we've got it here. All right, good question. Okay, I'd like to talk about one more thing before we start today's material. This whole idea of concavity being a this thing where the concavity changes from like frown to smile. We called it an inflection point. Did I mention that? Inflection point. Okay, let me show you something valuable about an inflection point because I think it's just something that would be worth pointing out. let's say that this is time and this is profit, okay? So you're looking at your business, and what you're realizing is that as time has gone on, you know, let's change it from time to number of employees. This is a totally made up problem, all right? But let's just think about what's going on here. It looks like from this graph that your profit goes up the more employees you have, right? The more employees you have, the profit's going up. Yes? You could tell me that for this function, the first derivative is always bigger than 0. Yes? First derivative is always bigger than 0. Function's always going up. But there is a point here, somewhere around here, where your concavity changes, where you actually go from a smile to a frown, right? And that would be your inflection point. This would be where your second derivative is 0. That's what's happening right here. Over here, your second derivative would be what? And over here, it would be what? So to the left, it would be what? Positive, and over here, it would be negative. So let's talk about what the value of that point is. So let me start back when we only had a few employees. Let's look at the slope of the tangent line here. We already know it's positive, don't we? Yes? We're making money, right? Profit. Making money. I add a few more employees. Am I making money still? Yeah, but I'm making money at an even faster rate, aren't I? Yes? And as I move on, right, it looks like I'm making money at an even faster rate. I get to this point right here, tangent line has a certain slope. As soon as I move past that point, am I still making money? Yes. Has the rate gone up or down though? I'm actually making money at a slower pace, but I'm still making money. This in business is called the point of diminishing return. Have you ever heard that before? The point of diminishing return? You're still getting return, okay? You're still making money here, but it's diminishing now. As I go out, I'm still profiting, but I'm profiting at a slower rate. So in business, we're often, they are often concerned with finding where that point of diminishing return is. Okay? Just wanted to point that out. Like, why do you need an inflection point? Who cares? It's useful in different things. Business, you can tie that to all sorts of things. All right. Today, we are doing graphing, curve sketching. We bring it all together here, and then we do optimization. We're supposed to have a test a week from today. A week, 28th, Tuesday. A week from today. Okay. Making sure I didn't lose. That's what's scheduled. That's the plan. Okay. I don't have any plans on changing that. So we got to cover this section today, right? And then this on Thursday, and then hope for a test on Tuesday. I may push it back, just depends, right? Yeah, see, that's what would be hard, is to get some sort of review in there. All right, so let's look at this curve sketching. Curve sketching, we could spend like an entire semester on curve sketching if we wanted to, but we're just going to get down the basics here. We want to see how you can sketch a curve completely from beginning to end using nothing but calculus and algebra and everything we've learned up to this point in mathematics, right? So how can I draw a very accurate depiction of a graph? Now, the reason why this would be kind of like, really, like, why do we have to go through all this is because technology is so great now. You know, I mean, back in the day, this is all we had. But then, you know, like if I wanted to do negative natural log of 2 over 3, I don't go break out a slide rule, do I? You don't know what a slide rule is? Show of hands. Anyone know what a slide rule is? Ever heard of a slide rule? It's before calculators. It's a wooden stick that they use to do math, like it's a calculator basically, and they had to slide the thing. It was like a logarithmic scale on there. It's beyond. I didn't use one, okay, and so I'll give you another one. How about an abacus? Have you heard an abacus? Okay, so like when you need to add up stuff, do you break out the abacus? No. If you need to graph a function, do you break out the techniques of calculus? Not often. You just go to a computer. Yes. I think that there's pros and cons, and there's reasons for and not. You always have to have somebody who understands underlying what's happening, because even the people who write the programs to draw these things, right? Even that, there's weaknesses. So you have to have someone that always understands the theoretical behind it. Like we graphed that one last class, and certain calculators drew both sides, others didn't. Okay? In order to figure out why it didn't, I would have to understand the program. Why did it not do that side? There are weaknesses in that program that didn't allow it to do it. If nobody understands what the theory is anymore, then you kind of lose trust in it. In engineering, we call this the black box method, or the black box. I call it the black box. This is the way my professor told me. The black box. Okay? So you have an engineer who wants to build a bridge. Here's a bridge. Okay? There's a road. There's some pillars. Big old bridge. You're going to put a bunch of thousands of people across this elevated highway every day, right? So they're trying to figure out structurally how things need to be built. So the engineer comes over here to his computer. This is a computer. And he puts in all the data of what he wants, and the computer spits out what he needs to go do, right? Like, okay, you need a bolt that's this big, this type of metal, blah, 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 right? If the engineer has no idea why, then that's very dangerous. Like if there's no physics behind it, like the computer's just doing an algorithm, right? There's no understanding of why, then eventually you get so far away from the theory that who's going to go back and undo the algorithm trying to figure out the theory now? I don't think that would ever happen, but there's a balance that has to happen. When I was in school, I had my project, my end of semester project for a class called numerical analysis, was that we had to take 3 different well-known popular math programs. One of them, Mathematica, that's what I'm using right now. I used Mathematica, MATLAB, and I can't even remember, so long ago. And we had to basically come up with a math problem that we knew the solution to theoretically, and then we looked at the code of the program and found weaknesses in it and exploited the weakness, and we were able to basically feed the black box a problem where it gave us an incorrect solution, and we could prove theoretically it was incorrect. So we were, you know, just showing the dangers of trusting the computer to over our own reasoning, if that makes sense. I don't know if I've answered your question. Mm-hmm. Yeah. 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 It's kind of like that. What I think you should try and get out of this, okay, is that the first derivative and the second, well, like in a college algebra class, the function itself told you a lot. You could find x-intercepts, y-intercepts. There were symmetry ideas. There was where the function was above and below the x-axis. Those were all things that you could do in a college algebra class. What you couldn't do in a college algebra class is tell me how high the function went, how low it went. That you couldn't do. Maybe for a parabola, but other than that, you know, sine curves you could. Theoretically, give me a function, I can find local max and minimums all day. I can tell you concave up, concave down all day. So the bigger picture is that the first and second derivatives tell you a lot about what a function is doing, how it's behaving. All right. Yeah, it is the essence of how the black box works. Now, whoever came up with the code for the black box, right? Whoever did that needed to understand the theory. But now the person using the computer doesn't need to understand the theory anymore. I like to bring up my calculus examples, don't I? Like my Cal 2. Oh, wait, I stopped doing my lectures in Cal 2 on video. Oh, well. We did a problem yesterday in Cal 2 where we were trying to show that a sequence of numbers was going down. And to do it, we actually converted the sequence over to a function, and we took its derivative and showed it was negative. So it's the understanding that the first derivative tells you if something's going up or down, right? That's kind of like, you need to understand that walking out of here. I'm going off topic. We need to get back on this thing. So here's what we need to do. Sketch a curve, right? Sketch a curve. So here are the steps. The book has a bunch of steps. This is what I'm going to break it down as, all right? We're going to find the domain of the function. That's the first thing we're always going to do. Just look at the domain of the original function. We're going to find any x and y intercepts like we did in college algebra. How do you find the x-intercepts of a function? X-intercepts. Set the function equal to 0. How do you find the y-intercepts if it has them? Plug 0 into the function. All right? Check for symmetry. Symmetry are things like x squared, parabola, right? Find asymptotes. How do you find asymptotes? Asymptotes are what's happening at the ends of your function, right? So we'll look at that. Determine where the function is going up and down or constant. That's not going to happen. But up and down we'll have. Find local maximums and minimum values and where they occur. Determine the intervals where it's concave up, concave down. Also determine inflection points. Make a table and sketch the curve. This is going to be kind of a final, we put all the information together in one picture and draw it. So we're going to start out with something very, very basic, just so you get the idea of how we do this. All right? And then after that, we'll go to something more elaborate. So let's sketch f of x equals 2x cubed minus 3x squared. And that's it. I mean, I'm going to keep it real basic. Now, from college algebra, this is what type of function? Polynomial function. So it, goes up, down, right? At the most it has 3x intercepts. So let's go through this process, see if we can get this thing sketched out. First thing, find the domain. What's the domain of this? All real numbers. It's polynomial. 2. What's the next thing? X and y intercepts. How about the x-intercepts? Set it to 0. Right? How about factoring out an x squared? Leaving me with 2x minus 3 equals 0. What are my solutions here? 0 and 3 halves. I should have 2 x-intercepts, 1 at 0 and 1 at 3 halves. Y-intercepts, or I said intercepts. You can only have one y-intercept if it exists. So plug 0 into the function, and what do you have? 0. So the y-intercept is actually the same as the x-intercept. It's the origin. We all good right now? Okay, next thing. Check for symmetry. Is this symmetric? What do you think? Does it look like I would have symmetry? One thing you can do to check for symmetry is this. Look at f of negative x. Plug negative x into this function. What happens if I take negative x and I cube it? Will it be positive or negative? It'll be negative, so this will be negative 2x cubed. What happens if I plug negative x in here and square it? It's positive, right? So this will just be negative 3x squared. The question is this the same as this exactly? No. If they were the same, what it would mean is that if I moved out to the right, positive x, it's the same as moving out to the left, negative x. So you would have this symmetric thing in both directions. That's not the case here. These two are not equal, so you don't have symmetry over the y-axis. Can someone give me an example of a function that's symmetric to the y-axis? X squared. Can someone give me an example of a trig function that's symmetric to the y-axis? Cosine. Cosine looks like this, right? But if I reflect it over the y-axis, it's the same thing. Cosine is an even function, right? X squared is an even power. Even functions are symmetric, and that's what I was checking for right there. If f of negative x equals f of x, if these two are the same, it is symmetric over the y-axis. But there's no symmetry here. If you're having trouble getting symmetry, just skip it. I don't want this to bog you down. Symmetry is one of those things where if you see it and it is symmetric, then you just remember that. That's all. But if it's something where you're like, I don't know, then just move on. 4. So what's the next thing? Find asymptotes. Let's first look for vertical asymptotes. Vertical asymptotes would happen anytime you have a fixed number over 0. Remember when we were doing limits and we said we had fixed over 0 that went to infinity or negative infinity? So where a function would go like this, you know? Do we even have division anywhere in here? No. So, nope. I'll put NA for not applicable. Doesn't apply. It's a polynomial, right? So no worries there. How about horizontal asymptotes? For this, you have to check 2 things. First, check out the left side, then check out the right side. How in calculus do I figure out what's happening out the left? I take a limit. I let x go to, if I want to go out the left side, negative infinity of the function. 2x cubed minus 3x squared. Understand what I'm doing? I'm saying, how does this thing behave as I go out to the left? So let's just plug things in here. If I let this number right here become infinitely large and I cube it, and it's negative, it'll stay an infinitely large negative number, won't it? So what I have is a form that looks like this. I've got like a negative infinity, then I've got minus, that's this minus right here. If I plug negative infinity in here and square it, it becomes positive. Then times 3 is positive. So we have like a positive infinity, but being subtracted. What's negative infinity take away negative infinity? Negative infinity. Which means that as I go out to the left, the function's doing what? It's going down to the left, right? As I'm moving out to the left, right, as I go out that way, the function's diving down to negative infinity. Yes? So there's no horizontal asymptote, but I know it's going down to negative infinity. What's happening out the right side? So go the other direction. That's a different limit. Limit x goes to infinity of 2x cubed minus 3x squared. Where does that go? So infinity cubed times 2, infinity, and then minus, what? Infinity squared, infinity minus infinity. Uh-oh. What's infinity minus infinity? That's bad. Right? I tell you about my daughter telling me that infinity minus infinity was 0. I was like, I said, we'll talk about that later, is what I told her. I said, for right now, let's worry about just numbers, regular numbers, you know? I mean, it doesn't make sense to a 5-year-old, you know? 5 minus 5 is 0. That they get that. Infinity minus infinity should be 0. But it's not. So what do we do when we see infinity minus infinity? We have to do something, right? Pardon me? That is correct. She knows that. She would answer that. If you asked her, she would tell you it's not a number. She's okay with that. Okay, so this, right? Infinity minus infinity, I try and factor it, turn it into a product. So I pulled out an x squared, and I've got a product now. This goes to infinity times infinity, that's infinity. So even though I couldn't tell here, I just did a little bit of work, and now I can tell. It's kind of bringing a lot of things together, isn't it? Some calculus instructors believe that curve sketching is one of the, benchmarks for a course like this, because you can really imagine giving a problem where this limit would require L'Hopital's rule, where it would be quite involved. So you can kind of bring a lot of concepts together into one place. Questions? What does this mean? Right side, it's going up. Now, look, back in college algebra, all they told you to do was look at this. If it was an odd power, it did either this or this, right? And then what you did is you looked at the leading coefficient. If the leading coefficient was positive, it did that. If the leading coefficient was negative, it does this. Do you understand that the calculus view on that whole thing is much more advanced than in algebra? In algebra, we're not answering the question of why it's that or that or that. And if you give a college algebra student something other than a polynomial, they can't handle it. Where here, we can, because we have the limits going up both ends. So this is the easy function. We'll do one that's harder where we have to think about these limits a little more. Questions? Okay, find the asymptotes. Got it. Determine where it's going up and down. So I'm going to need to do some derivative time, right? Okay, so where is this thing? Where is f increasing and decreasing? Let's figure it out. Take my derivative. I forgot the function. What was it 2x cubed minus 3x squared? So the derivative is going to be 6x squared minus 6x. That's it. I need to find out where that's 0 and where it's undefined. Where is it 0? Just pull out a 6x, be left with x minus 1. So where? 0 and 1. Is there any place where the derivative is undefined? Nope. What did we do after we did this. Number line. 0 and 1. That breaks up my number line into 3 separate sections. And I'm going to pick test points. And I'm going to plug these in. Oh man, I have to plug in a fraction. Oh well. Hey, another little idea here. I mean, we could plug these in, couldn't we, and get the answers? But this is my derivative, right? My derivative is a parabola, isn't it? And I'm trying to figure out where this thing is positive and negative. But which way does this parabola open? Up. So can you imagine just like transposing the parabola we have on top of that? Like graphically, that's what we have, right? A parabola that opens up, and these are the two x-intercepts. So I can already tell you where the parabola is above and below. Now, do your test points, though, because that only worked because it was a parabola. So plug -1 into the derivative. -1 in here, you get positive, which means my original function is going up. Plug 1/2 into here, figure it out, you get negative, which means your original function is going down, and then you plug in 2, it's going up. Now I'm just going to trust that you can do that on your own. Is that all right? Plug in those test points. They're going into the, test points are going into the derivative, right? -1. -1 squared is 1. -1 here, it's -6 times -1 is +6. So, okay, now I can tell from this, right, where I'm going to have local max. Local max at what? 0, local min at 1, right? Okay, but I'm just going to wait on that. Now let's go to the second, yes. That, I was looking at the derivative, though. I wasn't looking at the original function, right? Okay. Let's take a look at the second derivative. Now we're going for concavity. What is the second derivative? 12x minus 6. Set that equal to 0, which means x is 1/2. Right? X is 1/2. Anywhere where the second derivative is undefined? Nope, right? Number line, 1/2. Breaks up my number line to 2 sections. Pick a point to the left, pick a point to the right. Plug those into second derivative. Second derivative. Plug 0 into the second derivative, I get negative, right? What does that tell me? The original function is concave down. Negative people frown. Plug in 1 into the second derivative, I get 12 minus 6 is positive. That means the original function is concave up here. Do I have an inflection point? A change in concavity? It's happening at 1/2. By the way, I didn't look at this, the 1/2, the 0, and the 1. I never bothered to check those into the original function because in the beginning, remember we said the domain was everything? So I'm not worried about any of these like causing any problems for our function. But if the function were different, I would have addressed that. Okay, we good? Let me go back to this. Find local maximum values where they occur. Determine intervals with concave up and inflection points. Now the table time. This is kind of a big deal here, all right? This piece right here. Because everything I pretty much have done up to this point is stuff we've already done, right? Except for the beginning, which was domain, and then symmetry, x-intercepts, y. We haven't done that, but you did that, classes before this. So this is where we put it all together, right here. So the way this is going to work, just so you know where I'm headed, I'm going to draw, like if this is your piece of paper, I'm going to draw a table up here. This table is going to tell me about the graph. So the graph is going to be right below the table. So I would start on a good, clean sheet of paper here to try and put all this information down. You ready? Yes? Okay, what I'd like for you to do is about, I don't know, quarter of the way down the page, I'd like for you to draw a number line. And on this number line, I want you to put your critical numbers for both your first and second derivative. What were your critical numbers for your first derivative? Zero and 1? What were the critical numbers for your second derivative? A half. Put that there. Now from this, I want you to extend these up. And then I'd like for you to come over and draw, we're making a table. This table needs to have 3 rows. You'll always have 3 rows, all right? The number of columns will be determined by how many critical numbers you had. Y'all okay with this? Now, on the first row on the bottom, I want you to put F prime. Then I want you to put F double prime above that. And above that, I want you to put F. And I know that that doesn't make a whole lot of sense that you would go in that order, but just do that if you don't mind. We're going to do the first derivative on the bottom, then the second derivative, then the original function. So one way to think about this is we're going to first use the first derivative to figure out what it looks like, then use the second derivative to kind of tweak it a little bit, and then the final picture will be this. So let's now go through each of these rows and tell me, first of all, about the first derivative. Right here in this little region, to the left of 0, what did we say the first derivative told us? So to the left of 0, here's my first derivative, right, up, down. To the left of 0, what was my original function doing? It was going up, right? So look, I'm going to put here up, like that. What is happening between 0 and 1/2 for the first derivative? Between 0 and 1/2. Well, it's decreasing. Actually, it's decreasing all the way till I get to what? 1. So I'm going to come back over here and I'm going to say it's decreasing here, but it's also decreasing here. Do you follow that? Like I'm just extending it. And then after 1, it does what? Goes back up, increasing. You see how I use that information? Okay. Second derivative. Same thing. Move across here telling me second derivative. So what is happening to the left of 0 according to the second derivative? It's down. In fact, it's down all the way till I get to what? 1/2, and then it goes up. So it's going to look like this. Down here. It's going to look like down here. It'll be up here and up here. You okay with that? This is where it changed, right? Here, and then over here for the first derivative, it changed here and here. No questions? The final row is where we get the final piece of what the graph's going to look like. So I know that my function f has to look like a frown in this region to the left of 0. It must look like a frown, but it must also be going up. So think about a frown for a second. It cannot look like the whole frown, right? Because it goes up and then it goes down, right? The only way to look like a frown and be going up is if you were looking at just the left side of the frown, correct? So that's what I'm going to put above here. The left side of a frown is what the function should look like to the left of 0. Now, what about in this box? I've got to look like a frown, but I've got to be going down, right? So now it's the other side of the frown, right? The right side of the frown. So it's got to look like this over here. Then, how can you be smiling, concave up, but be going down? Left side of it. Left side of the smile. And then you need to be going up on the smile, which means you're now going to look like the right side of a smile. You all see that? The red pieces on top tell us exactly what our graph should look like. Now, below this, what I'm going to do is I'm going to translate that down to my real x-axis. So this is going to be my picture below it. I'm going to put my y-axis, which is right here. And I'm going to plot the points, my critical numbers, 1/2 and 1. This is supposed to come straight down, you know, like it's supposed to be a direct translation just straight down. 0, 1/2, and 1. Now, let's put in some information. Did we have any x-intercepts? Where were our x-intercepts? Zero and 3 halves? Where's 3 halves on my picture here? Well, this is 2, right? So 3 halves would be right around here. Those points live on my graph for sure, right? Agreed? All right. Now, from this information here, 1/2, I would actually like to know what my function's doing at 1/2. And I would also like to know what it's doing at 1. Because these are where I had changes happening, right? At 0, 1/2, and 1. So I'm basically going to plug 0 in, 1/2, and 1. Now, we already know what happens when you plug 0 in. But what about 1/2 and 1? Let's go do those. And I'm plugging these into the original function. What's f of 1/2? What's f of 0? No, we already did 0. F of 1. I'll do f of 1, you do f of 1/2. Sound fair? Where's the function? Is this the function way back here? Okay, plug in 1, we get -1. So I plug in 1, I get -1. 1, I get -1, not 1/2. What do you get when you plug in 1/2? What do you get? -1/2? Y'all okay with that? That's going to be right around here. Do we have any questions? Sure? Plugging these numbers, 0, 1/2, 1, into the original function. What does my function do on the ends? The right side, it goes up forever. I'm just going to draw a little guide for myself here. It goes up forever and down forever like that, right? That's what it should look like. Now I'm going to start putting all the pieces together. Looking straight down here, right, from 0. To the left of 0, I've got to look like this, right? So starting from this point, I'm going to draw the left side of a frown, like that. And does that kind of match what I said it would do? Yes. Now, between 0 and 1/2, I'm going to look like the right side of a frown. And look that means I've got to connect this point to this point, right? With the right side of a frown. Is that all right? And then from this point to this point, I have to look like the left side of a smile. So it's got to go like this. And then from this point, the rest of the way, it has to be this, right? Right side of a smile. But I've also got to go through that x-intercept. There it is. Okay? Now, the original was 2x cubed minus 3x squared, right? I guess I should. See, in college algebra, does anybody remember doing this in college algebra? Where you would do this thing called multiplicities, where you could tell that the x-intercept, you would bounce off the x-axis, or you would cross through. Do y'all remember doing things like that? It was a long time ago. Okay, and I don't know, I have students in my college algebra class that ask me, like, how do we find out how low that point is? Like, how do I know that? You can't until you get to calculus. But not only do we know where this point is, I mean, our graph is pretty darn close to that, right? I mean, we are pretty good when you compare those two, right? There's not much of our graph that doesn't look right. We've got the correct curvature here. We've got the correct curvature between here and here. We've got the lowest point. I mean, right? Get it? Okay, that only took like 30 minutes. So my kind of question now is, how bad do we go now from here? Like, how ugly of a function do we want to look at? Call it a day? What? What's up? That's it? That's it? That's all you want? I think that the only way that you could truly appreciate this is to do a function that you really wouldn't know what it looked like without this. You know? Like, that's a polynomial. You kind of knew what it looked like. So let's try something that wouldn't be so obvious. It's a little bit different. I didn't put negative x up here. Okay, you ready, everyone? Do you want to look at it first? No? You don't want to look at it first? Okay. I kind of want to look at it first. No? You don't want to look at it? All right, all right. Okay, you ready? First step, domain. All real numbers. All right. X-intercept, Y-intercept. Does this have an x-intercept? You have to set the function equal to 0. I'm going to factor an e to the x out of both of these. Right? In the problem I was asked about for the homework, this was very close to the same problem, except it was negative x up here, and I think that was a plus. So it's not the same function as what you were doing for homework. So we can do this instead of what I did earlier. Now set each of these equal to 0. When I set those each equal to 0, is it possible for e to the x to equal 0? No. Is it possible for e to the x minus 1 to equal 0? Yes, if e to the x is 1. But that'll only happen when x is what? 0. E to the 0 is 1. You could have taken natural log on both sides. The natural log of 1 is 0. So we have one x-intercept. Yay. How about a y-intercept? You just plug 0 into the function. And when you plug 0 in, you should get e to the 0 is 1 minus e to the 0 is 1. 1 minus 1 is 0. So the origin is a point on our graph. Questions? What's our third step? Symmetry. Forget it. Let's just skip it. Fourth step. Asymptotes. All right. Do you have any skip it. Sketch it. Table. Skip. We're done. Let's go. Vertical asymptotes. Do you have any places where you have fixed over 0? No. Right? You have no fractions here. Horizontal asymptotes. All right, you have two limits you have to look at. The limit, as x goes to negative infinity of e to the 2x minus e to the x, and the limit as x goes to positive infinity of e to the 2x minus e to the x. In both cases, well, no, the first case, what happens when I plug negative infinity in here? What's e to the negative infinity? What does the exponential function do as I head to the left? Goes to 0, right? So this is headed to 0. E to the negative infinity is headed to 0. Minus e to the negative infinity again is headed to 0. So this is headed to 0 minus 0, which is 0. That's okay. So it's headed to 0 to the left. How about this? Positive infinity. What's e to the positive infinity? Infinity minus e to the positive infinity. Infinity. Infinity minus infinity? Bad situation. But I can factor, right? This factors e to the x out. Now what do you get instead of infinity minus infinity? Infinity times infinity, which would be infinity. So this is headed to infinity. So the left side is going where? Out the left of the graph, it's headed towards 0, but out the right side, it's headed towards infinity. So it almost looks like an exponential function. It should. Questions? 5. Are we on number 5? Step 5? Okay, increase, decrease time. So for our fifth step, I need a derivative. The derivative is 2e to the 2x minus e to the x. What do I need to do with that derivative? Set it to 0. So I need to set 2e to the 2x minus e to the x equals 0. How are you going to solve that? Factor in e to the x out. Good. And then I've been doing teacher observations all this week. Did one last night. I had to come back up to school last night and do one. That's why I was here. Did one this morning. I have another one today. I have another one tomorrow. I don't know how y'all sit through these classes. It's ridiculous. Hour, 40 minutes. I remember as a student, but I'm kidding. No, I mean, but none of them were calculus and they weren't fun, you know? Oh, man. All right, so look, what do we get here? Do we set e to the x equal to 0? Is that going to have a solution? No, but how about this one? This should, right? 2 e to the x minus 1 equals 0. Move 1 over, divide by 2. X is a natural log of a half, which we did that earlier, right? Oh, no, that was my other class. Never mind. Sorry. Natural log of 1/2 is natural log 1 minus natural log 2. Oh, no, we did do that, didn't we? Never mind. But we didn't have that 1/3 in there. Okay. So we have a solution at negative natural log 2. Everyone good? All right. How about where the first derivative doesn't exist? Any issues with the first derivative? Any problems here? Nah, we're okay. Nope. But I have to consider it, right? I have to think about it. Next, number line. Negative natural log 2. Test points. Zeros to the right, I know that. And we did negative natural log of 2 earlier. I think if I do negative 10, I'll be safe. I think that's far enough to the left. That reminds me, I have to do a faculty evaluation after our class. I apologize. I think it's 3. What's the class that starts after this class? 3? 3:30? It depends, doesn't it? Is it 3:30? Yeah, something like that. So I might have a little bit of time after class. I don't know. Like, I know where I'm going. I know who I'm observing. I don't know what class it is. The one I did today was stats. The one I did last night was 3:10. Oh, no, it's only math. Oh, no, I could wind up in another class too. It depends on the type of evaluation that's being done. So we all get evaluated. It just depends on how often. So I think we all have to have yearly, but some of them are by semester. Let's not get into it. You want me to pause my video? I'll pause my video. Did you already figure this out? What's it doing? E to the 0. I'll do 0 first. 0, 2 minus 1, positive. Going up. Function's going up over here, right? And the other side's going down? Yeah? Is it? You sure? Negative 10. What's e to the negative 10? Well, it's a positive number. E to the negative 10, it's about 2 over, yeah, that's going to be negative. Okay, f's going down. So we look like we have a local minimum? All right. What do we need to do now? Second derivative, right? And do the concavity thing. So second derivative, is what? 4 e to the 2x minus e to the x? Set that equal to 0. When I set that equal to 0, can I factor an e to the x out right now? All right? Okay. I think we're going to get, after you do a little work here, x is going to be natural log of a 4th. Because you'll move the 1 over, you'll divide by 4, you'll do natural log of both sides, and you'll get this. Which is going to be really natural log of what? Negative natural log of 4. And then there was no solution from setting e to the x equal to 0. Number line this. partition, test points. Zeros to the right. I think negative 10 will work again. Those are getting plugged into the second derivative. Positive. When I plug in 0, I get positive. So that tells me the original function is concave up here. Negative 10 in here. I think the same thing happens. We should get a negative. Y'all with this or not? I mean, you all seem like you're getting it, but it's a lot of work, right? I mean, it's just a long process. A lot of room for error. Imagine if your derivative's off, right? Your derivatives are gone. I mean, you're done, right? You're cooked, right? All right, I'm going to move on now to the table. So I'm going to start a fresh page. What do I put on the number line for this table? Just the critical numbers. So what was the first derivative critical number? Negative natural log 2. And then the other one was negative natural log 4. So which one's where? Which is where? Is negative natural log 4 to the left? Okay. Just make sure you're okay with that. That's negative. Put those are the only two I had, right? What if you miss one of your critical points? Your graph's going to be all whacked out, right? So we've got F prime on the bottom, F double prime's next, F on top. Where does my first derivative change? Was it negative natural log 2? What is it doing to the left of negative natural log 2? It told us we were going what? Down? And then it went up? Okay. And then the second derivative told us that the original function was concave down and then up. After negative natural log 4. So up here, up here. Now I'm going to highlight where these things are switching, right? The first derivative switched at negative natural log 2. The second derivative switched at negative natural log 4. That's why everything to the left of this is down, to the right of this concave up. We okay? How do you go down a frown? Which side of the frown are you on? Down a frown. Right side. How do you go down a smile? Left side. How do you go up a smile? Right side. It's the basic behavior of what our graph's going to be looking like. We just got to paste things together properly here. So below this, I'm ready for my graph. Where were my x-intercepts? Did I have an x-intercept? At the origin at 0, which is over here to the right somewhere. I had an x-intercept. Did I have a y-intercept? Same thing, right? What is my graph doing as I go to the left? It's going towards 0. So remember that as I go here, as I go out this way, right, it goes to 0. That means getting closer to the y-axis, isn't it? What about going out the right side? What did it do? It's supposed to go up to infinity. So just keep that in mind as we draw this, okay? Now, what am I supposed to do? I mean, I want to get a picture, but what am I supposed to do to get this picture? Plug these points in to the original function. So it's time for me to do that. I don't think I can avoid it anymore. So I have to do f of negative natural log 2, or how about this? I'm going to switch it back. Wasn't that what it was, like that? And then I switched it to negative natural log 2 and negative natural log 4. If I plug this into this, minus, why did I put 2's there, not 4's? You okay with this? I switched this back. Is that all right? Now I'm plugging this in here. This one should be pretty easy, right? What is e to the natural log of 1/4? Just 1/4, right? The e and the natural log cancel out. So I know I've got a 1/4 out here. All right. This one right here, how about we move that 2 up as a power and make it squared on the 1/4 instead? Is that a legitimate move? In front of a log? Numbers in front of logs can go up as powers. Powers can come out of logs. So what does the e to the natural log do here? Cancels out. What's 1/4 squared? 1/16. What's 1/16 minus 1/4? Negative 3/16. Okay, that's that one. Do the same process for this next one. You should get like 1/4 minus a half, which is negative 1/4. That means that negative 3/16 is a little bit closer to the y-axis, to the x-axis than this one is, right? Which one's bigger here? Negative 1/4 is just slightly bigger, right? So when I go to my graph, anybody get those as a decimal, what those are? Negative 1. Negative 0.18. So let me say natural log of 2, negative 0.25, which would be here. And the other one is a little bit smaller, so it's a little bit above that. Do you all see that? I'm kind of exaggerating it. This one right here, I went out and I went down negative 3/16. This one I went over and I went down negative 1/4, which is a little bit further than a negative 3/16. And that should be all I need. I'm going to put the left side of this graph together. So to the left of negative natural log 4, it should look like this, right? Should look like this. So is this correct? No. Why? It's not supposed to cross the x-axis because we only have one x-intercept. It's down here. Further, it's supposed to get closer to 0, right, as it go out the left? So it needs to look more like this. But it's got to look like a concave down right side of a frown, which it does. And then when I get to here, it's supposed to connect these two dots, but it should look like the left side of a smile. So you kind of do your best here to make that look like the left side of a smile. I don't like that. It's because the points are so close together. What I'm doing is I'm going to move this one down just slightly to exaggerate it. There we go. That looks a little bit better to me, like the left side of a smile. And then once I get here, right side of a frown, right side of a smile, all the way through here, continuing that pattern and going up forever. There it is. And we check. It was e to the 2x minus e to the x. There it is. Now, where did we have that lowest point there? Right. Yeah, negative natural log of 2, which if you do that on your calculator, it should be this. Look at the, remember what the y value was? It was negative 1/4, negative 0.25. So I feel pretty good we got that. And then what you can't see from this is that inflection point, can you? I mean, you can see it, but you don't know where it is. I do not believe that this would be able to do it. Although this is pretty damn smart. You can actually ask it to give you the derivative of that one and graph it. And so if I find the extreme value of that one, it happens at, so basically this is just this point right here. That's happening at negative natural log of 4. Don't worry about it. Yeah. Okay, so how much time do we have? 10 minutes. That's a lot of time. Not to do another one, no. But to get you thinking about the next, look, we don't have a whole lot of time. You know, next class you're going to want to talk about other things like the test and stuff. So, are y'all done? Are y'all tired? I'm not sure yet. Oh, with the sketching, 1, and it will be probably an easy polynomial. Yeah. I want to see that you know how to do the process. That's all. Find 2 numbers. No, this is the next section, but it's not. We're not officially getting into the next section. I just want to talk about it. Find 2. Okay, we are going to start getting into optimization problems. Now, this is definitely not a real-world optimization problem, but it's going to get you to start thinking a certain way, hopefully. I want us to try and find 2 numbers that are both positive numbers whose product is 100 and whose sum is a minimum. So let's first just get our heads around what this thing is asking. You're supposed to find 2 numbers that multiply to be 100, right? And when you add them together, you want it to be the smallest possible thing. So I heard 2 and 50, right? Let me write 2 times 50. Everyone agree that that's 100? All right, but what's 2 plus 50? 52. Okay? What else multiplies to be 20 and 5? That's 100. What do those 2 numbers, 20 plus 5, add to be? 25. So which one was smaller? This one right here, right? These 2 numbers, I'm supposed to find 2 numbers that multiply to be 100, which I did in both cases. But whose sum, and the sum of those 2 numbers needs to be a minimum, the smallest it can possibly be. So I heard 10 and 10. 10 times 10, which is 100. And then 10 plus 10 is 20, right? This looks like it might be the best case scenario, which unless you can think of something else. You have to be positive. Yeah, I put that in the problem, both positive. Good, good. That's looking like it might be the best, right? But remember the race car problem? So sometimes the way it looks isn't the way it always is, right? So what we're going to need to do is try and translate this problem into a math problem. And then try and find a minimum. How do we find minimums? We look at the graph and we try and find the local minimum, right? Try and find the lowest point. So let's try and translate this problem into math in the next 6 minutes. Find two numbers. Okay, let me call them x and y. Right? X and y. What do I want to know about x and y? X times y must be what? 100. I also need x plus y to be a minimum, right? Well, I don't like the equals. How about an arrow? I want to find the minimum value of this. You got it? Okay, this right here, the thing we're trying to find the minimum of, or sometimes we're trying to find the maximum, this right here is called the objective. Either function or equation, depending on how we set it up. Look, if I tell you right now, hey, come up with two numbers that when you add them up, you get the smallest thing you can think of. Two positive numbers. Add them, the smallest thing you can think of. What numbers could you give me? No. Look, start from scratch. Brand new problem right here. Give me two positive numbers, or let's say not negative, that when you add them up, you get the smallest thing possible. 0 and 0, right, would work. 0 and 0, add them. I said non-negative, I changed it. So 0 and 0, yes? But so this by itself is not what the problem's asking, right? We want the minimum of this, but there is something else we want, right? We need this to be true, don't we? We need the product to be 100. This right here is called the constraint. Does it make sense that that would be called the constraint equation? So it's like, let me go back and rephrase that question. Give me two numbers that when you add them up together, you get the smallest thing possible. But they have to multiply to be 100. That's the constraint. That now changes what you're allowed to use for x and y. Yes? Any questions? So I'm going to call this objective function right here. I'm going to call it S for S for sum. Do you agree that the sum of those two numbers is x plus y? This is my objective function. This is my objective equation. I want S to be the smallest it could possibly be. Right now, in order to find S, you must know x and y. Yes, two different things. But if I take this equation right here, my constraint, and I solve it for x or y, I'll solve it for y. What do you get? Y is 100 over x. And now, if I come in here and rewrite S, I can write x plus what? 100 over x, can't I? Replace y with 100 over x. And now I can even go as far as saying S is not just any old variable. S is actually a function of x, isn't it? The only condition I have here is that x must be positive. And so this problem that I posed has now been translated from a word problem to a function. a function on an interval that goes from 0 to infinity, and I want you to tell me where that's the smallest it can be. Understand? Bonus to be turned in on Thursday. Find the minimum value of that function, right? That's what we're asking. We will do more of that on Thursday, but you know, our problems are going to be more applicable to real-world stuff, I guess. Yeah, you should graph some stuff, huh? I'll keep it pretty simple, but I'll also challenge you to try some of the harder ones. For 4.4 homework, page 230. I would say 1 through 17 odd is a lot of problems, all right? But I think those are all like fair test problems. Because the algebra on those stays kind of okay. I recommend you just, you know, knock out maybe one of them. There's a mixture of polynomials and rational functions there. Like do one of the polynomials, then try one of the rational functions. And then go back and do another polynomial, another rational. Because they take so long. Okay. Have a great rest of your